All right, warm up. Raise your hand if you already looked at the warm-up question and noticed something. It is factored, right? So that's nice that it's already factored for you. If you are having trouble with factoring, please remind me next class on our review day to give you some extra factoring problems, okay? All right.
Is it in the review day next class?
Yes.
Wait, we're gonna take this?
Quiz. Okay. It's factored. What else do we notice about those factors?
The top and bottom.
The top and bottom match everything?
No.
What matches?
X minus 7.
X minus 7. If you have the same factor on the top and the bottom, what can you do? You can cancel them. Okay. When we are graphing and we get a term that cancels like this, it creates a hole in the graph. The problem with this hole is that even though Desmos sees that hole, it's almost impossible for you to see the hole on Desmos, because what is the size of a single point? A single point is infinitely small. So if you're looking at Desmos and you're thinking, I would like to see this point that is a hole, you will not see it because it's infinitely small. If you tried to find the value of that point, it wouldn't be there because, we factored this out, and then we found that the 0 of x minus 7 was x equals 7. That's the x of the hole. We're going to substitute that into our reduced function, which was x plus 1 over x plus 9. So 7 plus 1 over 7 plus 9 gives me 8 over 16, or 1/2. That's not such a bad number. So my hole is at 7, 1/2. When we graph that hole, not only are we not capable of graphing infinitely small, also I would never be able to see that. I have bad eyesight as it is. So we do actually graph our hole as like an empty dot that actually has some size to it. What else do we need to find? We need to find our vertical asymptote by finding the zeros of the remaining factors in the denominator. So the denominator factor that canceled out created a hole. The denominator factor that's left creates an asymptote. So that one would be x plus 9 equals 0. So it would be an asymptote at x equals -9. Find the horizontal asymptote. See the directions in the day 5 notes. So in the day 5 notes, we had those detailed directions about if the degree of the top is bigger, if the degree of the bottom is bigger, if the degrees are the same. What would you say about the degrees of the numerator and the denominator? They're the same. And when they're the same, we take the coefficients of your leading term, 1 and 1, and you create that fraction. 1 over 1 is 1. So it's just going to be y equals 1 in this case. And then it says find the x-intercept by putting 0 for y in the reduced function. So it would be 0 equals x plus 1 over x plus 9. We solve that by multiplying both sides by x plus 9, and that times 0 is still 0, so it goes to 0 equals x plus 1. And then we get x equals -1. So my x-intercept was -1, 0. And then to find your y-intercept, you put 0 for the x in the reduced function. So it would be y equals 0 plus 1 over 0 plus 9, which is the fraction 1/9. And that would be the point 0, 1/9. Okay, so we didn't actually graph that one, but we did do all of the features of it. All right, so let's do an example together. What's the first step? Factor. So we need to find numbers that multiply to -20 and add to -1. Don't say them out loud. You're going to put them on your paper. And then numbers that multiply to 4 and add to 5. I want you to take a moment and try to factor those. Let me know if you have any questions. All right, Precious, what did you get for the top?
X plus 4 and X minus 5.
And Taryn, did you factor the denominator?
Yeah, X plus 1, X plus 4.
Thanks. All right. So we did step 1. Actually, we didn't cancel yet. Does anything cancel? Good. So here's my reduced function. I guess I could have put it right here, right? But I don't have to write it twice. It's up to you. So my reduced function is f of x equals x minus 5 over x plus 1. All right, I'm going to find the whole from the canceled factor. So I'm looking for the whole right now. The canceled factor was x plus 4. So if I write x plus 4 equals 0, I get x equals negative 4. So I know that the x coordinate is negative 4. How do I find the y coordinate? Thanks, Steph. Put the x value into the reduced function. So I'm going to have negative 4 minus 5 over negative 4 plus 1. I'm getting negative 9 over negative 3. What's negative 9 over negative 3? 3, good. Hello. Thanks. All right, vertical asymptote comes from the remaining factor or factors in the denominator, and I have x plus 1. That means my vertical asymptote will be x equals what number? What number would make this denominator 0? Negative 1. X equals negative 1. Yes. Now you can actually show the math for that. You can write, okay, x plus 1 equals 0. Subtract the 1. X equals negative 1. But if you know that's what it is, you can just write it. For the horizontal asymptote, we need to consider the degree of the numerator and the denominator. The degree of the numerator and denominator, are they the same? Is the top bigger? Is the bottom bigger? Remember, degree comes from the highest exponent. What's the highest exponent on the top? Exponent. 1. And what's the highest exponent on the bottom? 1. So they're the same. So when they're the same, it is going to be the ratio of the leading coefficients. Leading coefficient is 1. Leading coefficient is 1. That means my horizontal asymptote is y equals 1. The tricky thing about that is it's a totally different rule if they have different degrees. That comes from the last class notes. All right, for the x-intercept, you make y what? Make it 0, good. So for the x-intercept, we're going to make y 0. So I'm going to do that over here. 0 equals x minus 5 over x plus 1. Multiply by x plus 1. What's 0 times x plus 1? 0. All right, so my x-intercept is 5, 0. For my y-intercept, I set x equal to 0. All right, your end behavior, you can know that even without looking at the graph. Now, for some of these, you might choose to look at the graph on Desmos, and I do encourage you to check yourself on Desmos. But the end behavior is always going to be which asymptote? The end behavior of a rational function is going to be which asymptote? Look at some of the graphs in the back you got that 6th period made last class. Look at the end behavior. Is it going to the horizontal asymptote or the vertical? It goes to the horizontal. So as x goes to infinity, y goes to our horizontal asymptote 1. And as x goes to negative infinity, y goes to our horizontal asymptote, which is 1. All right, so for the whole, we're going to take the x minus 2 that we canceled out, set it equal to 0. And when we add 2 to both sides, we get x equals 2. Morning. Then we're going to take that 2 and we're going to substitute it into the simplified function 2 plus 6 over 2 minus 4. And I'm getting negative 4. So for my whole, I got 2 comma negative 4, and I graphed this empty dot at 2 negative 4. All right, your vertical asymptote. Take what remains in your denominator, the x minus 4, set that equal to 0, and we get x equals 4. For your horizontal asymptote, the degree on the top is the same as the degree on the bottom. So you're going to take your lead coefficients 1 over 1, and you should have y equals 1. All right, so I'll do the x-intercept up here. For your x-intercept, you make y 0, so y is the f of x. Y equals x plus 6 over x minus 4. The nice thing is that because the y is 0, when you multiply both sides by x minus 4, 0 times x minus 4 cancels out. Another way to think about this is when you're thinking of a fraction that equals 0, it's just the numerator that has to be 0. It doesn't matter what the denominator is. 0 over 5 is 0, 0 over 10 is 0. Either way, we get to 0 equals x plus 6. And then we have to subtract the 6 to get x equals negative 6. And you have to write it as a point. The point will be negative 6 comma what? 0, good. For the y-intercept, I'm going to make the x 0. So y equals 0 plus 6 over 0 minus 4. So I get 6 over negative 4. What does that simplify to? Negative 3 over 2, or if you like to do it as a decimal, that's okay too, because decimals are easy to graph. But if you're good with fractions, negative 3 over 2 is good too. So we want to graph those two intercepts as well. So I graphed -6, 0 and 0, -1.5, and I can draw a branch on my graph now. Remember that the graph is going to get close to your asymptotes without actually crossing them. It might cross the horizontal. We can check that on Desmos, but usually it doesn't. It will never cross the vertical. So we're missing something on this graph. What are we missing? We didn't do that part. Yes. Alexa?
Oh, wait, I have a separate question.
Okay, go ahead.
If I missing something, can you by any chance?
Yeah, I can. Ask me at the end of class, okay?
Okay, thank you.
And note that class ends a little bit early today. Yes.
How are you supposed to know that you wrote the computer graph?
We're going to check on Desmos. Pretty much. We can't check the whole, really. You can kind of check the whole. Okay. All right. We are missing something on our graph. What we're missing is the branch on the right side of the vertical asymptote. You will have a branch on both sides of your vertical asymptotes for rational function. You won't just have one side. I don't know where it is precisely, but I know it's up here, okay? I can get a point on that graph by substituting in an x value. And usually I just pick the next one. So here's 4 for my asymptote, so I would pick 5. And I'll substitute it into this to find out the y value. So if I want to know the point where x equals 5, I can substitute it in, and I get 5 plus 6 over 5 minus 4, which is 11 over 1, which I believe is going to be like way up here. So it means that there's a point at 5, 11. That just gets me 1 point on my graph. And then I'll sketch the rest in. I know that this is going to be the shape. It's going to be getting closer to my asymptotes. Okay. When you have a hole in your graph, that is going to be cutting into your domain and your range. So my domain actually is going to have 3 pieces to it. I'll have the piece that goes up to the hole, and then the piece between the hole and the asymptote, and then the piece from the asymptote to infinity. So I have 3 parts to my domain. The first one starts over here at -infinity, and it goes till the x value of my hole, which is 2. I got to leave that out because it's empty. Okay, then right after the hole, it keeps going until I get to the asymptote. I have to leave the asymptote out. And then I need to start up again after 4 and go to infinity. Now to do the range, bless you, it would be helpful to know if I cross that horizontal asymptote at all. So I think before we do the range, let's just graph this in Desmos and see how we're doing. When you graph it in Desmos, don't graph the simplified one, graph the original one. Okay, so we graphed it in Desmos. We noticed that it looked a lot like what we did. Had the right intercepts. It seems to have the right asymptotes. The hole is something that we don't see unless you are able to land like right on that 2 and see the undefined. It's kind of tricky. But we're going to do our range. So our range starts at the bottom at -infinity. And then it goes up to the y value of the hole, -4. -4 up to my asymptote. And then from my asymptote, it should go up to infinity. Okay? As x goes to infinity, y goes to what? It would be if it didn't have that asymptote holding us in. Blaine says 1. What do you think? Yes. So the horizontal asymptote is your end behavior. You got to remember that. The horizontal asymptote is your end behavior. All right, so when we factored it, we did find that this cancels, and that's the factor that creates the hole. So we have a hole with an x value of -1. We get that from x plus 1 equals 0, x equals -1. So the canceled factor creates the x of the hole. Then I got to substitute that back in to find the y of the hole. So -1 minus 1, -1 minus 3, -2 over -4, quiet please, which is 0.5. So your hole is at -1, 0.5. Your vertical asymptote comes from the remaining factor in the denominator. X minus 3, if you set that equal to 0, you get x equals 3. And in our reduced function, we have the degree of the numerator and denominator are the same again. Because these two are 1, you take the lead coefficients of 1. And we're going to get another horizontal asymptote at y equals 1. It is not always y equals 1. It was just a really easy one to make an example of, but it's not always going to be y equals 1. We're going to save our domain and range. We're going to do our intercepts. So for your x-intercept, we make y 0. So I'm going to do that over here. 0 equals x minus 1 over x minus 3. Some of you are skipping this step where we multiply both sides by x minus 3, and that's fine. Because you see that that's going to cancel, and we just get 0 equals x minus 1. And we get x equals 1. So my x-intercept is going to be at 1, 0. If you need to, yeah. Your y-intercept is going to be where you make your x 0. So I'm going to take this function here, and I do 0 minus 1, 0 minus 3. So I'm going to get 1/3. So I'm going to graph this, and then we'll figure out our domain, range, and end behavior. So I'm going to graph my asymptotes at x equals 3, y equals 1. My intercepts, x-intercept is at 1, 0. Y-intercept is at 0, 1/3. And then I have a hole at -1.5. And so you're going to draw this branch in. For our purposes, you are allowed to sketch the other branch in, but I do like to just find a point on it. So if I substituted 4 into this function, I would get 4 minus 1 is 3. 4 minus 3 is 1. So I would have a point at 4, 3. And I can sketch in this branch. Okay. Domain. For the domain, I need to leave out the hole and the asymptote. So I'm going to have 3 pieces. -infinity up to the hole at -1. -1 up to 3. And then 3 to infinity. For the range, I'm going to go all the way from -infinity up to my hole, which has a y value of 0.5. There's this tiny piece between 0.5 and 1. And then it goes after the asymptote 1 to infinity. Your end behavior is your horizontal asymptote. As x goes to infinity, y goes to 1. And as x goes to -infinity, y goes to 1.